Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we defined Z transform of a discrete time signal x of n as x of z equals to summation n minus infinity to plus infinity x of n z to the power minus n, where we considered z equals to r e to the power j omega, which was the generalization of the exponential e to the power j omega used for discrete time Fourier transform. So Fourier transform of a discrete time signal and Z transform of a discrete time signal will be same when Z is equal to e to the power j omega or when r is equal to 1. So we define Z transform of the impulse response as the transfer function of the system. Impulse response is the time domain characterization of a linear time invariant system, and transfer function, which is the Z transform of the impulse response, is the frequency domain characterization of the same linear time invariant system, and transfer function generalizes the frequency response characterization of the system's input output behavior. So definition of transfer function in terms of input output behavior of LTI system is: transfer function is defined as ratio of the Z transform of the output to the Z transform of the input, and this offers new insights into system characterization in the frequency domain. Now we'll consider applying a discrete time signal x of n as an input to an LTI system whose impulse response is defined as h of n. Now, because this is a linear time invariant system, output will be convolution between the input and the impulse response. So, convolution summation will be written as y of n equals to summation k minus infinity to plus infinity h of k x of n minus k. X of n minus k is the reflected and shifted version of the input signal. So, we'll consider input signal to be an exponential defined of the form z to the power n. We defined z as r e to the power j omega for z transform. So if we use z as r e to the power j omega, this will be an exponential signal itself as an input. So for this input signal, convolution summation can be written as y of n equals to summation k minus infinity to plus infinity h of k z to the power n minus k. If we decompose z, z to the power n will be independent of this summation, so it will be taken outside, and the remaining summation k minus infinity to plus infinity h of k z to the power minus k is defined as a transfer function of the linear time invariant system, which will be denoted by h of z. So the transfer function h of z will be summation k minus infinity to plus infinity h of k z to the power minus k. In terms of input output, or the output of linear time invariant system will be given as y of n equals to z to the power n h of z. Now z to the power n was the input applied to linear time invariant system, and we are getting the same output. So z to the power n is the eigenfunction and h of z is the multiplying factor to it on the output. So h of z is the eigenvalue. If you look at these two input output relations, convolution is the output of a linear time invariant system in the time domain. If we use transfer function to obtain the output, then the output will be multiplication of the input signal with the transfer function h of z. So one more use or usefulness of z transform is, to obtain output in time domain we'll have to perform convolution, which is a complex operation. If we use Z transform, then the same output of linear time invariant system will be obtained as multiplication between the input and some multiplying constant. In this case, it is a transfer function. So convolution operation will be reduced to multiplication. So we know that in Z transform, Z is defined as r e to the power j omega. Now we'll use this expression in transfer function to obtain the inverse Z transform. So using r e to the power j omega in place of z in transfer function, we can rewrite it as h r e to the power j omega equals to summation n minus infinity to plus infinity h of n of r e to the power j omega to the power minus n. If we rewrite the exponential inside the summation and rearrange the terms to separate out the real part, then h r e to the power j omega will be equals to summation n minus infinity to plus infinity h of n r to the power minus n will be combined together. E to the power minus j omega n will be the exponential. Now if you observe this summation, it is the standard definition of discrete time Fourier transform for the signal h of n r to the power minus n. If this is the Fourier transform of the signal h of n r to the power minus n, then the inverse discrete time Fourier transform of the spectrum h r e to the power j omega must be equal to h of n r to the power minus n. So to obtain this discrete time signal h of n r to the power minus n as an output, we'll use inverse discrete time Fourier transform we saw in module 4. So inverse discrete time Fourier transform for the signal h of n r to the power minus n will be written as 1 divided by 2 pi integration minus pi to pi h r e to the power j omega of e to the power j omega n integration with respect to omega. We'll be using integration because the spectrum h r e to the power j omega will be a continuous one, and the limits are from minus pi to plus pi because the spectrum will be periodic with respect to 2 pi as we studied in module 4. So to simplify this, we'll be multiplying r to the power n on both sides. So left hand side will be h of n. Multiplying r of n to the right hand side, the integral will become r to the power n divided by 2 pi integration minus pi to pi h r e to the power j omega of e to the power j omega n integration with respect to omega. If you send r to the power n, or if you combine r to the power n with the exponential, we can rewrite the integral as 1 divided by 2 pi integration minus pi to pi h of r e to the power j omega r e to the power j omega of n integration with respect to omega. And we know that for z transform, z is equal to r e to the power j omega. If we differentiate this, dz will be equals to j times r e to the power j omega d omega. If we rewrite this for d omega, then d omega will be equals to 1 divided by j z inverse dz. Now for limits minus pi to plus pi mean z traverses a circle of radius r in the counterclockwise direction, because we know that z plane is a two-dimensional plane where r is the radius of a circle and omega is the angle made by it. So using all of the results in the above integral, we can rewrite it as h of n equals to 1 divided by 2 pi j closed integral h of z to the power n minus 1 dz. Now this closed integral is integration around the circle of radius defined by r. Mod of z will be equals to r, which will be the radius of the circle. So in general, the transform pair, z transform pair, is defined as for any arbitrary discrete time signal x of n, the forward transform z transform will be defined as x of z equals to summation n minus infinity to plus infinity x of n z to the power minus n. This will be the forward transform. This gives this transforms time domain signal into frequency domain signal. And the inverse transform is defined as x of n equals to 1 divided by 2 pi j closed integral x of z to the power n minus 1 dz. This is the inverse transform. From frequency domain signal, we'll be obtaining time domain signal from this expression. And now we'll see how to represent the Z plane. Just like S plane, Z plane is also two-dimensional. On y-axis will be representing the imaginary variables, and on the x-axis will be representing the real values of Z. And because we are representing Z in the polar form, r e to the power j omega, r will be the radius. Because r is radius, the region of convergence on the Z plane will be a circle. If r is equal to 1, then mod of z will be equals to 1, because mod of z will be, if it is equal to r, it is a circle. If r is equal to 1, then it will be a unit circle. Then region of convergence, or the values of z that will be evaluating for the z transform, forms the closed path. So always region of convergence for Z transforms will be a circle, will be represented by the circle. So on the Z plane, the values on Z that will be evaluated will be represented on the circle. So this circle designates the region. Inside of this unit circle will be one region, and outside of this unit circle will be another region, which will be used to define the nature of the discrete time signal, or which will be used to define the Z transform x of z. We'll be looking into the details of this region of convergence in the next class. So Z transform is defined as x of z equals to summation n minus infinity to plus infinity x of n z to the power minus n. If we use z r e to the power j omega in place of z, then we can rewrite it as x of z equals to summation n minus infinity to plus infinity x of n r to the power minus n e to the power minus j omega n. If you look at the summation, then it is the Fourier transform, discrete time Fourier transform of the signal x of n r to the power minus n. Now with the help of this expression, we'll understand the usefulness of the Z transform. Fourier transform, which is defined by this expression, x of z equals to Fourier transform of x of n r to the power minus n. Fourier transform of the discrete time signal x of n may or may not exist, but Fourier transform of the signal x of n r to the power minus n may exist with the proper choice of r, meaning x of n r to the power minus n may be absolutely summable, where just the discrete time signal x of n may not. Therefore, because of this reason, Z transform is more versatile compared to discrete time Fourier transform. And the region of convergence, now the definition of region of convergence is, region of convergence are the values of Z for which the summation of the Z transform definition becomes absolutely summable. It becomes a finite value. So values of Z for which the summation takes a finite value are called as region of convergence. So region of convergence shall depend only on r and not on omega. It depends only on the radius, not on the angle omega. So this is the most useful character of the Z transform compared to the Fourier transform. Now, what is the region of convergence? What is the nature of region of convergence, and what are the properties of region of convergence? We'll be going through in the next video lecture. Thank you all.